Everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Today, USound are coming back to talk to us and give us some updates on their progress with their MEMS speaker technology. But let's give thanks to the Alti Association, a great networking and audio industry organization. So we encourage people to get out and join that association. So let's get into the discussion. And Simon Weston in Japan. Good afternoon, Simon.
Good afternoon.
And we got a couple field application engineers from USound, Konstantin Davy and Andrea Greco, or Andy, as we call him, I guess. So good morning, guys. How are you?
Morning.
Doing good.
Okay, so as we prefaced, we don't need to give people the full background on USound. We did talk with you guys a few years ago, and now you're back to give us some updates on the MEMS speaker technology, and how are things going for you guys. So I guess I'll just throw it over to you guys and let us know where you guys are at in terms of your technology deployments, and what are some of the things that you guys have discovered or learned and overcome in your process.
Hi again, David. Hi, Simon. So this is already the second podcast with USound. Therefore, you and the whoever is listening know already a bit about our company. However, I will give a very brief introduction again for whoever was not present during the third podcast, and then we will delve a bit more into the details of today's presentation. So very quickly, USound is an Austrian company with headquarters in Graz and offices also in Vienna and in China. It's been founded in 2014, and it's actually been the first company to have MEMS speakers on the market. We have filed over 300 patents on MEMS speaker technology. And then our products include, other than speakers themselves, also amplifier and audio modules. With respect to last time, we now have available a new family of MEMS speakers, which is called CONAMARA. We will give some details later on. And also a couple of product releases, a new ASIC, a linear amplifier, which is called Tarvos, and then several integrated audio modules with different type of layouts and applications.
Okay.
So very in short, now our products catalog has been it's bigger, and we have. So last time we talked with you about our Ganymede series, which is our first family of MEMS speakers, initially developed for in-ear applications, but also free field applications such as augmented reality, virtual reality glasses, smart eyewear, and so on. And they have the characteristics also to be available without any ferromagnetic materials. And this is quite crucial because it allows for some very peculiar applications such as MRI headphones and so on. And now we have expanded our portfolio with a second family called CONAMARA, which I will describe later on. And it's our most compact MEMS speaker solution, mainly for TWS earphones, in-ear monitors, Odyssey hearing aids, and so on. We have designed in-house our new ASIC, which is a linear audio amplifier designed specifically for our MEMS speakers in order to improve power consumption and performance. And then a combination of the two, which is an integrated audio module called Core, which combines in a single plug-and-play product our speaker, in particular the CONAMARA speaker, and our amplifier. But we will show you a bit better later on.
Okay.
And then, so the one I introduced earlier, they are specifically USound only product, but we have also now in our family other two products which are integrated modules with two speakers, so two-way systems in a coaxial arrangement developed with two important companies. One is called Gemini, developed with Luxshare, and the other one is called Grape, developed with Concraft, OBO Pro 2 from Concraft. And Konstantin will better describe their.
We'll go into detail on these a little later. Yeah.
Correct.
Correct.
So just as a quick recap for those that have not seen MEMS speakers before, and what we mean when we say MEMS speakers, MEMS is a manufacturing technique, it's not a transducer principle. So what we do is we replace the traditional voice coil and magnet with a MEMS, with a silicon die, which is produced with a certain way so that when we apply voltage, it can move. It's based on piezoelectricity. This movement is then transferred onto a diaphragm, and this diaphragm is then what radiates the air. The reason why we're not moving the air directly with the MEMS element itself is because with MEMS technology, with silicon technology, you have an incentive to keep the area small in order to keep the cost low. Because the cost of silicon, of course, scales directly with area. The more units you can fit in a wafer, the cheaper every single unit gets. That's why we designed our speakers to have the smallest possible piece of silicon. And in order to still have a large acoustically effective area, we pair it with a relatively normal diaphragm. So that's how we make all of our MEMS speakers. The animation that you see on the screen, in case you're watching this on video, is from our first generation of speakers, or first family of speakers. The new one has a different form factor, but the principle behind it is the same. So we have Greco actuators that create movement. The movement is transferred into a diaphragm, and the diaphragm is then what radiates the sound. So benefits of MEMS speakers, just in general, as a recap again, the main idea why you would even use or start developing MEMS speakers is because you can make them much smaller. That's the main benefit. Of course, you still need the same area roughly in order to produce sound. But in terms of volume or thickness of the speaker, since the motor unit that moves the diaphragm is much thinner, because silicon is much thinner than a voice coil or magnet, we save a lot of space. That's up to 75% of volume reduction compared to voice coil speakers. With that also comes a decrease in moved mass. So we have a much lower moving mass, which means that we have a much easier time with high-res audio or with very high frequencies. All of our speakers can play up to the ultrasonic frequency range. In the lab, we measure up to 80 kilohertz. We stopped not because our speakers cannot play there, but because our measurement equipment cannot produce any stimulus above 80K. And we do have ultrasound applications as well for some of our speakers, like distance sensing. So even though we did not develop them for ultrasound, they still work perfectly fine in there. Power consumption is also a big topic with MEMS speakers because they have a capacitive load, so power consumption works a bit differently. But with specifically designed amplifiers, it's possible to reach less than a milliamp current consumption. That's the value that we reach with our ASIC. It's 0.9 milliamps. Since the stiffness of the MEMS speaker is determined mostly by the MEMS element, that also means that we can use different diaphragms than what you would usually use for electrodynamic speakers. That means we have a much easier time withstanding water pressure or high pressures. So our speakers are inherently water resistant up to IPX8. We tested them up to 3 meters, and that's not a problem. So if you want to have a product with IPX8 certification, then with MEMS speakers, that's very easy to do. Okay. With normal speakers, you have this, the water pressure can become an issue for the membrane. Also, another big issue with traditional speakers is, since you have a magnet present, you cannot heat them above a certain point, because if you cross the Curie temperature of the magnets, then they will demagnetize. Our speakers don't have magnets, so we can heat them up to higher temperatures. The limiting factor is the glue, and that's something that can be engineered around. So what that means is that we can use reflow soldering processes with our speakers. And this enormously reduces manufacturing cost for the product, because you don't need to solder the speakers by hand. on a hand assembly line, you can do it fully automated, right? You just have your PCB, run it through the reflow oven, and put the speakers on there, just like any other component. That's a big reason to use MEMS speakers. The part-to-part consistency is extremely low as well, since we use semiconductor processors, which are very precise. We get less than a decibel variation over most of the bandwidth, which has some benefits, like you don't need to match individual speakers anymore. You can just use any one and pair them, which is also nice for manufacturing. And then, as Andy said, we do have the option to not use any ferromagnetic materials, meaning not using any metals that can be magnetized, which opens it up to some applications where you need high magnetic strengths, magnetic fields, such as the headphones that you use in MRI machines. That's admittedly a small market, but it's a market that we have tightly under control.
Mm.
So,
yeah, thank you, Konstantin. And this is, now we can go a bit more into the details of our product updates. As mentioned earlier, we have now a second family of MEMS speakers called CONAMARA. In this case, with respect to the first family, the main difference now here is the form factor. So CONAMARA have a very slim and round form factor, and they are characterized by having a very, very slim silhouette. Now, as you know, the thickness of a MEMS loudspeaker is negligible with respect to traditional electrodynamic speaker, which are made of coil plus magnet. And in our case, or in the case of MEMS speakers, the only actual limiting factor to the thickness is the excursion of the piezo motor, right? So this allows USound MEMS speakers to be as thin as roughly 1.4 millimeters. So as you can see here in the slide, the CONAMARA speakers are available in two variants with two different diameters. Both of them are almost equally slim, so the thickness is about 1.4 millimeters. One is available as a 6 millimeter diameter, and it serves as a full range speaker, or it can be used as a tweeter, while the second variant is available as a 5 millimeter diameter and is mainly used as a tweeter. As Konstantin mentioned, they are IPX rated, therefore they can be perfectly used in a wet environment, or where there is, for example, high humidity or sweat, or even underwater. And they provide a very high bandwidth, so they can be used also in high-res applications. And last but not least, basically the advancements in diaphragm technology now allowed the CONAMARA speakers to withstand temperature high enough for reflow soldering. And this lowers the cost of manufacturing because it reduced the need for manual labor and allows for fully automated assembly lines. So this can save up to 50% costs in the long run. Yeah, so this is basically in a nutshell our new family of speakers.
So, with MEMS speakers are great, and they have a lot of upsides. They also have some downsides, or some things to be mindful about when using them. Like, you cannot just use them as a direct drop-in replacement, because for a couple of reasons. Like, their impedance is mostly capacitive. In the audio band, it's fully capacitive, right? So they behave like a true capacitor, meaning that their impedance is very high at low frequencies and very, very low at high frequencies. So this is not something that every amplifier can easily deal with. They also require a higher input voltage, around 10 times more. It's not as as high as you need for electrostatic speakers, but you definitely need a higher voltage than you need with electrodynamic speakers. That's just because the piezoelectric force is slightly weaker than the electrodynamic force. And on top of that, some of our speakers, not all of them, but some of them do need a DC voltage. And that's, again, something that typical amplifiers, audio amplifiers, are not capable of providing. Of course, there is an easy solution for that. You just develop an application-specific IC. That's what we did. So that's why we have what we call the Tarvos amplifier. It's essentially an analog.
Sorry, quick question, if you don't mind. When you say it needs a DC voltage, you mean that the supply signal must be biased? You can't
correct. So the AC signal has to the AC, so the audio signal has to be shifted up so that, for example, when you have an AC voltage of, let's say, 5 volt peak, so it has a voltage swing of -5 to +5, then it needs a DC voltage of at least 5 volt DC so that the actual voltage never drops below 0. That's an issue because you, depending on the type of piezoelectric material that you use, if you go too much into the negative voltage range, then the material starts to depolarize, which of course messes with distortion and has a bunch of nasty side effects. That's something you definitely want to avoid. So that's why you need the DC voltage to bias the voltage to a point where the complete voltage swing is always in the positive range. That being said, our second generation of speakers, so the CONAMARA speakers, work without a DC voltage as well. The reason for that is we use a slightly different material. You can imagine there is a lot of IP and R&D in there. It's still PCT, but it's a different way of doing the crystals so that they don't depolarize with negative voltage. So up to the maximum voltage range that we specify in the datasheet, they can also work without a DC. It changes the sensitivity of the speakers a bit. It changes the distortion levels slightly, so you get a slightly higher sensitivity and you get slightly higher distortion. But if you look at distortion over SPL, it's roughly the same. So it's the sensitivity that changes mostly, which makes it easier to use because you don't need the DC anymore, but you still need the higher input voltage. So for most applications, you will still need the application-specific IC, the Tarvos amplifier as we have it. Right. And then one more limitation that is just inherent to this type of speakers is the stiffness is depending not just on the diaphragm as it is with electrodynamic speakers, it is also depending on the MEMS itself, right? Because the MEMS is connected to the frame and then in the middle connected to the diaphragm. So it is part of the system stiffness. And in fact, it is the dominating factor of the stiffness of our speakers, which means that we cannot arbitrarily lower it as much as we would like to, because we still need to transfer the force from the actuators onto the diaphragm, or even for those speakers that don't use a diaphragm, we still need to move the piezo cantilevers. So there needs to be an inherent stiffness in the speaker, which limits just some applications. For example, at very, very low frequencies, like below 500 hertz, there's a certain limit to how much SPL you can get. While this is sufficient for many applications, so for many full range applications, we can produce like 110 decibel. That's enough for many applications, like hearing aids or so, where you don't need an enormous amount of bass boost. There are applications where you need much, much more sound pressure at low frequencies, like noise canceling, that type of thing. For these applications, we use two-way systems, and that's what we're going to go into a little later in more detail, which allows us to use, somewhat traditional electrodynamic speakers, but since we use them in a two-way application, they don't need to. We can afford for them to lose some performance at high frequencies, but gain some performance at low frequencies, because we use then a traditional MEMS speaker for the high frequency range. So it's a little more high performant than a single electrodynamic speaker could do. But we'll show some about that in the next slides.
Can I ask quickly about about the stiffness, I think. The stiffness is higher, is what it's implying. And to what extent, say, a small earphone speaker, something comparable, I guess, in the system, the fundamental resonance might be like a kilohertz or something like that. Are you significantly higher than that?
We have two types of MEMS components. The one is optimized for full range applications, where we typically target a resonance frequency of between 2 and 3 kilohertz, because that's where you need the peak anyway in an in-ear headphone.
Yep. That's in situ. That's built into an earphone, or is that a free field resonance?
That is in situ, yeah. So measured in the standard ear simulator.
And then
we also have
the stiffness being a bit higher and so on. Does it imply also that the effect of acoustic fluid is less significant? You mentioned that the stiffness is dominated by the MEMS element. Is that also true? So the difference between a free field and in an earphone is also less than it would be for a dynamic traditional speaker?
To some extent, yeah. So correct. So the movement, if I understand your question correctly, is that the movement of the sound producing element, so the membrane, is less affected by the acoustic load. Yeah, that's true. We still see some effect. Like if you load them differently, you still see different movements. So you cannot predict it just as a perfect velocity source, but there is less influence on the movement of the diaphragm from the acoustic load. It's comparable to, let's say, balanced amateur speakers, which also have a little less effect than electrodynamic speakers. And then we also have these speakers with a higher resonance frequency for 5 to 6 kilohertz, which we use as tweeters. Of course, these have an even more increased stiffness, with accordingly a lower SPL at low frequencies, but we use them as tweeters.
Mm-hmm.
Right. So we mentioned two what we call solutions, two developments here. First being an ASIC, the second being the two-way systems. But first, we'll talk about the ASIC a bit. It's with you, Andy.
Yeah, thank you, Konstantin. So the first solution we implemented is this ASIC, which is called Tarvos. It's a linear audio amplifier. It's been designed to drive all USound MEMS speakers, right? So as the name suggests, its input is analog, and it's compatible basically with all the most common Bluetooth audio SoCs, and it operates from a standard 3.6 volt lithium-ion battery, which is standard and ideal for all the TWS applications. And one of the main drivers for the design of Tarvos was to maximize the power efficiency, mainly at low-medium sound pressure levels, so like below 80 dB, because this is the range which represents the most typical audio content and where most power consumption reduction is required. And this allows the battery life and playtime to be boosted considerably. Also, Tarvos has a flat and extended frequency response, not only in the audio range, but up to around 40 kilohertz. So it can also work in the ultrasound frequency for applications such as high-res audio. And it allows for very, very low, so under 1 milliampere quiescent operating current, which is one of the best in the market so far, and integrates a DC-DC boost converter. And it's basically based on an audio class H amplifier, so you can select the gain from, at the moment we have 3 steps, so 18, 24, and 30 dB, so that you can adapt the output of the amplifier depending on the input you have in order to provide the maximum output SPL to the speakers. And last but not least, it allows for a very, very low THD and the floor noise. So the THD, as you can see here, is below 0.2% at maximum voltage. So it means that it completely does not have any impact, any influence on the audio chain and on the performance of the speaker itself.
So a Class H amplifier, is that a switching amplifier? Is it pulsing?
No.
So it's basically, it's a differential amplifier, and it has a mechanism which is called dynamic control. So basically it starts from this 3.6 volt battery, and then it adapts the output whenever the input exceeds a certain threshold. Then it adapts the output in order to follow the input. So that basically until you are within the 3.6 volt, it only uses the battery, and then it uses the DC-DC boost to provide any excess energy you require for the output.
Okay. But it's not a switching mode amplifier, no. Okay. That's one thing with switching mode amplifiers. You have quite you have the switching noise at very high frequencies, which when you connect them to a capacitive load, they would draw a lot of current from the amplifier, right? Because the capacitive load has very, very low impedance at high frequencies. So this could actually cause the amplifier to overheat or to go into some sort of limit. That's why switching mode amplifiers are a little trickier to use, or are actually not recommended to use with MEMS speakers. If you need to use them, then you need to figure out some form of low pass before you go into the speaker.
Okay, well, I'll ask this slightly differently. Is there some characteristic of a Class H amplifier that's suitable for driving a capacitive load?
Well, the fact that it does not emit switching noises is the main issue. Yeah, and it allows us to increase the power efficiency a little bit by changing the supply voltage.
You see.
Yeah. Cool. Right. The next logical step.
And then, basically, this is a very, very interesting application because USound MEMS speakers are PCB based. So it means they can be easily combined with additional SMT, so surface mounted components, to form an audio module. And this is our integrated audio modules, which has been designed basically to showcase the modularity potential of USound technology. So it's not an actual product, it's more of a reference design that can be adapted and customized to the specific customer needs. And it allows customers to speed up and improve their development cycle. So it can be used either in the lab or as a prototype or a product mock-up and so on. And it basically combines, as you can see here, it combines the CONAMARA speaker, so our round-shaped MEMS speakers, 6mm, with the Tarvos ASIC, mounted back-to-back on a PCB with all the required passive components included. So it's basically a plug-and-play system, which makes much easier the design for the customer, because you don't need to think about the integration of the components. Everything is already there in the product. And also at the same time, it allows for a evaluation of the product, because it has inside both the amplifier and the speaker, you can evaluate the complete audio signal chain. So either on the amplifier and the speaker performance. So yeah, basically this is our module combining the two products we have introduced earlier on.
Yeah, again, the idea is really just to place the amplifier or the ASIC directly on the back of the loudspeaker. So you have the closest thing you can get to a plug-and-play solution. Of course, you still need to provide the amplifier with a power supply. You just connect it to the battery. But yeah, that's the idea behind that, placing the amplifier directly on the back of the speaker. It's still thinner than a traditional electrodynamic speaker. Like a usual 6mm electrodynamic speaker would be roughly 6mm in thickness as well. This is less than half that, closer to a third. So we save quite a lot of space with that.
Okay.
Right. So this is useful for let's say PSAPs or OTC hearing aids, where you need the full frequency range, but what you mostly need is the clarity at 1 to 8 kilohertz. For those applications where you need an enormous amount of SPL at low frequencies, we have partnered with other companies. So that's what this is about. We have 2 developments actually going on with essentially the same goal. One is done with Luxshare, the other is done with OBO Pro. Those are both somewhat established companies. They make a few billions of revenue and supply to the big players. And what they have come up with is a electrodynamic speaker with very, very low compliance. So very, very high compliance, very, very low stiffness, which allows them to have quite high excursion, which in turn gets them to a very high performance for low frequencies. The trade-off for this is that both of those speakers don't perform quite as well at high frequencies. So we've worked together with them to insert our speakers together with their speakers in a coaxial arrangement to create a audio module that combines 2 speakers. So it's a two-way system. This is the idea. It's not a fully new invention. The novel thing is doing it in a coaxial arrangement with micro speakers. It's not easily visible here on the pictures. Maybe you can see that so the electrodynamic speakers that both these companies developed are ring radiators. So they're shaped like a donut. They have a hole in the middle, and the diaphragm is like a torus. And in the middle of this ring, so in the middle of this torus, we have a space available, and this is where we place the MEMS speaker as a tweeter. So they they radiate from the same acoustic plane. It's a coaxial two-way system. The idea behind that is I think decently well known. So the benefits of that is it allows you to develop a speaker, an electrodynamic speaker, where you can trade off performance at high frequencies, but gain performance at low frequencies. That's something that you need, for example, for noise cancelling applications, where you do need the speaker to be capable of producing 130 or more decibel. Of course, just for small peaks, but you still need the speaker to be able to produce that, and you need very, very high leakage tolerance. So the movement of the speaker needs to be capable of adapting depending on the acoustic load, because with noise cancelling systems, you typically want to use them in a very leaky environment, at least where the front volume is vented, more so than on traditional speakers, so that the noise cancelling system works more precisely. And for this, the speaker needs to be quite leakage tolerant. And if you can sacrifice high frequencies, then you can develop speakers that can fulfill this requirement very, very nicely. And of course, then to play the high frequencies, both of those companies decided to use our MEMS speakers. So that's how we ended up there.
Okay.
Hey, what's the tube for on the top one?
Right. So that's for those that are not seeing this. Actually, showing this on the next slide. So it's a coaxial arrangement with the woofer being in sort of a donut shaped, and the speaker being placed in the middle of this donut and then playing through the middle. For one of those modules, we have this tube that is sticking out from the plane of the tweeter through the woofer. The idea is that depending on the design of the earphone, the outlet of the woofer and the outlet of the tweeter will play into the same volume of air, which at frequency ranges just above and below the crossover region, where they are not fully in phase anymore, because at the crossover they're the same phase, but then above the crossover they will have different phase angles. So above the crossover frequency, the movement of the membranes will be out of sync, right? So by placing the tube in front of the tweeter, we increase the distance between the two, and therefore reduce this. It's sort of an acoustic short circuit, right? So you get a drop in level because the air is only being pumped forward between the two. So by inserting the tube, we can eliminate that. This can be done with other solutions as well. But for this module, we have this tube. Of course, the angle of the tube will depend on the application. So depending on how you fit the speaker in the earphone, the tube will have to be at an angle. This is just the very first drawing we did for the proof of concept.
Yeah, so it's it's mitigating the phase cancellation around the crossover point.
Above the crossover point, exactly. At the crossover, of course, they're at the same phase, by definition. But above that, you get some phase effects which are mitigated with these solutions.
Right.
Yeah. So this is the what we call the Gemini module. It's developed together with the department of Luxshare. So Luxshare developed the woofer, we developed the tweeter, and then we together developed the combination of those into a module. For this module, the woofer and tweeter will have separate inputs. So it would expect the SoC to have a digital crossover and then drive the woofer and tweeter separately. This, of course, would mean that you could do things like apply the noise cancelling signal only to the woofer and not to the tweeter, therefore reducing some of the intermodulation effects, and then applying the music signal to both of the speakers, things like that. So if you want to be very, very smart about how to play your signals through a two-way system, then with the Gemini module, you can make use of the separate inputs of the two speakers. Of course, you can also add a crossover, an analog crossover after your SoC output. That works just as well. The size of the module is, we have two options. The first option we developed was nominally 13 millimeters. It's a little under that, it's 12.5. And then a lot of our customers required a slightly smaller module. So we have a second option which is just below 11 millimeters in diameter. There is an option to get a forward-facing microphone directly on the module itself. Although we find that most customers prefer to have this separate of the module so that they're more flexible with placement. Right. And then the second development, it looks very similar. I just choose a few different pictures, was done with Concraft, or with the OBO Pro division of Concraft, which is slightly smaller. It has a 10 millimeter diameter and is also quite a bit thinner. It's like 3 point something millimeters in thickness. And this one has the crossover and also the ASIC, so the amplifier for the MEMS tweeter, built into the back of the module itself. If you can see it on the video, there's a small PCB at the back of the speaker, or the PCB actually forms the back of the speaker. And there's the analog crossover as well as the amplifier for the MEMS. So this is the closest thing you can get to a plug-and-play solution where you just need to provide the power for the amplifier and then a single audio input for the speaker. Samples for those will be available in Q3. For the Gemini modules, the samples are available basically now. Yeah. So since you asked about the tube, you will note that the tube is absent from this design, which means that, of course, you still need to avoid this phase issues at above the crossover frequency. So what we do for that is, so this is a picture of the reference earphone with the module inserted into the earphone. You can see that there's two separate tubes. So the idea behind that is to use the volume of air in front of the woofer only to create a Helmholtz resonator that creates an acoustic low pass above the crossover, but below the frequency where the phase cancellation occurs, right? So we reduce the level of the woofer above the crossover, therefore eliminating or reducing the effects of this phase shift. As you can see, it does not take up a lot of space. It's essentially just the volume of air in front of the woofer that you would have to use anyway in order to place it. And using that, it's basically just a question of introducing a small feature with a hole which creates this resonance, and then joining this together with the tweeter signal into the spout of the earphone. Yeah, of course, the exact design will depend on the industrial design of the final application. That's our reference earphone, which just easily shows how to do that. Right. What do you think?
Excellent. So this, just if you don't mind, this crossover cancellation, phase cancellation of having a two-way system. Is that something that I'm not all that familiar with it? Is that something that can only be handled acoustically, or is a digital filter prior to the system able to deal with that problem?
Sure. So the only thing that you need to do is prevent one of those speakers from producing SPL at this frequency range, right? Because if only one of them is playing, then they're not pumping air back and forth. Since this is something that happens above the crossover frequency, it is the woofer that needs to be not playing there. So of course, with an electric crossover or a digital crossover before the speakers, this is reduced by the same amount. With the acoustic crossover after the speakers, before the final output, this is further improved without the need for extra steep filters in the electric domain.
Is there kind of a magic filter that eliminates it completely? I mean, you say, well, you should have this incredibly steep filter, but that just changes the point at which the phase becomes opposite, or is there a way to actually eliminate it totally? In theory, perhaps.
In theory, also we did not try that. We went for the simple solution with the standard crossover with available components, and then an acoustic crossover to further improve it. Is there a way to fully eliminate it? Well, I'd have to try it out.
This got to be the same issue for all loudspeaker manufacturers, isn't it? Do they not have to deal with the same problem?
To some degree, yeah. But with larger hi-fi loudspeakers, you can typically make steeper crossover filters because you can easily fit more components in. With micro speakers, you are quite limited in the amount of space you have available, even with SMT tech.
Okay. Then in terms of the MEMS microphone, we may have already covered it, but just again, the acoustic characteristics of the device, are they more or less the same as a voice coil speaker, or something different? For example, do you still place a filter paper, have some vent on the rear side, and place some damping mesh on that?
Yeah. So, if you just look at it as a black box, we have a device which is a few millimeters in size, which is the frontmost part of it is a diaphragm that moves, which produces sound pressure. So of course, this needs to be connected to the ear in an intuitive ear scenario to some degree. We do still recommend venting the front volume to equalize the static pressure. And of course, the back of the speaker, it's a diaphragm. Diaphragm is inherently a dipole. Back of the speaker also radiates sound. And this needs to be vented to the outside or connected to the front, again, to equalize the static air pressure. So yeah, vents are something that is still needed, just because we create sound pressure and we generally want to avoid changing the static air pressure in the ear. So we do vent them the same way. Yeah. What we don't need, so with the full range application, we require less of a volume of air behind the speaker. So because the VAS of the speaker is lower. So we don't need as much space behind the speaker as a traditional electrodynamic speaker would. Yeah, that's it. I think that's what we're getting at, right?
Yes, exactly. And then on this topic of stiffness, so what is the characteristic? What is the limitation there? That as you increase stiffness, the low frequency sensitivity drops proportionally. Is that
right? So I'm sure you're aware of the maths behind it. I'll just repeat it for listeners who haven't opened the textbook in a long time. Is the resonance frequency of any resonance system is determined by the mass and the stiffness, right? So if you increase the mass, then the resonance frequency will lower, and the amplitude above the resonance frequency will then lower. If you increase the stiffness, then the resonance frequency will go up, and the amplitude below the resonance frequency will go down. So generally, in a loudspeaker, what you want is, of course, zero mass So you have very, very high output above the resonance frequency, and you also want zero stiffness. So you have very, very high output below the resonance frequency. In the real system, as with anything in acoustics, you have to make a trade-off and see where the limiting factors is and where the beneficial factors are. Mm-hmm. So with our speakers, we do have a limit in terms of how low we can make the stiffness. We don't have as much of a limit in how low we can make the mass. Of course, we still need to have something that moves. So we do have the diaphragm, we do have the piece of silicon that moves. It's actually the silicon stem in the middle that has most of the mass. It's still negligible compared to the mass of a voice coil. We're talking fractions. So for all intents and purposes, we are not limited in terms of the moving mass, but we do have limits in terms of the stiffness, both because of the materials that we use. So, if you design your first MEMS speaker and you start with a basic piece of silicon or polysilicon as the base layer, then you're limited by how compliant or how stiff, how much non-stiff you can make the piece of silicon, essentially how thin you can get it. But of course, the thinner you can get it, the more fragile it gets. Of course, you don't need to use polysilicon as the base layer, even with MEMS technology. And in fact, we're not using silicon as a base layer, but still there is a second limit for stiffness that is required, because you still need to create the movement. And if you have if you had zero stiffness in the actuator, then the actuator itself would not be able to create any movement. That's different to electrodynamic speakers, because in the electrodynamic speakers, the part that creates the force is not the diaphragm itself, or it's not the actuator, it's the coil and the magnet, right? And the stiffness between coil and magnet is effectively zero, but can still transmit force because it's based on the electrodynamic force. But we're based on piezoelectric force, so we create the movement is created directly inside the piezo element. So this needs a certain stiffness in order to produce enough force. So that's the absolute limit for this type of technology on why we cannot achieve zero stiffness at all.
Okay, but then the converse, I was just saying the converse is true. Then you have a lower mass, so the high frequency sensitivity is relatively high.
Correct. We have a significantly by orders of magnitude lower moving mass than traditional voice coil speakers, because we are not moving a voice coil, which means that we can very easily play at high frequencies. There are, of course, resonances at high frequencies. It's not a perfectly flat frequency response up to 80 kilohertz. Although I say that, but with our second generation of speakers, we do have speakers that have an essentially flat frequency response up to like 70 something kilohertz. So we can use them for what's called wideband ultrasonic applications, where you play, it's essentially distance sensing, but instead of playing at just 40 kilohertz and recording the reflection, you play like an encoded signal, which then requires more than a monofrequency signal. So you have a wideband signal. And for this, you need a speaker that can play wideband signals at equal amplitude, or roughly equal amplitude at all frequencies. And that is, in fact, one of our applications. Yeah.
Okay. And how do you compare the sensitivity and, let's say, close to and above resonance to an electrodynamic speaker, in the sense that we say you might use SPL per milliwatt? Do you use the same kind of measure, or is it a bit different? It's not really burning off energy in the same way.
That's right. Yeah, because we don't really have a resistive component to the impedance. I mean, at some point we do, right? At very, very kilohertz or hundreds of kilohertz, at some point you get the resistive component just from the small piece of wire connecting the pad to the MEMS. That will have some resistance. It's not relevant for the audio portion. It's not relevant in the ultrasonic portion or the high-res audio portion, but there is very, very few resistive part. So no, we don't use decibel per milliwatt per se, because if you were actually to measure a decibel per milliwatt, you would get a very, very strong frequency dependency, because our impedance is not essentially flat. It's essentially that of a capacitor, which is 10 times or 1,000 times higher at 20 hertz compared to 20 kilohertz. So what we use is decibel per volt, and then compare this to traditional speakers. So at high frequencies, let's talk 3 kilohertz and up. So the treble portion, and especially the ultrasonic portion, there is very, very few speakers that we don't beat. So especially in the ultrasonic range, as we got to beat very easily. So for distance sensing applications, and that's one of our applications is distance sensing. Not so much for large distances. Ultrasound has limits in terms of range, but for example, for let's say AR or VR glasses or controllers, you could sense the position of your fingers or the position of your hands relative to the device with ultrasonic signals. For this, you would need encoded signals, so wideband signals. But that is one of the applications that we have. Yeah.
And then just a bit more on power efficiency. So, again, comparing to electrodynamic speaker where you're burning off power in a resistive load, some component of inductive load, but that's okay. Your speaker doesn't actually have that. It's approximates to a capacitor, in which case you're not really using any power. So how do you kind of quantify that power consumption of the speaker?
That's right. Yeah. So we found that the fairest comparison is, because for most applications you're not really interested in how much is being drawn by the speaker. You're interested in how much is being drawn from the whole system, right?
Yes.
So what we found is the fairest comparison is not to compare the power directly at the speaker, because this would again bring the issue of there not actually being any power. It's more like volt ampere and not actual watts. So what we do is we compare the current draw from the amplifier.
Okay, and then
because, with MEMS speakers you do need this amplifier in order to get to the higher voltages. And that's one of the reasons why we developed our ASIC, is to lower the power consumption, because there are off-the-shelf components available that can drive MEMS speakers. There's a few from TI and a few others, but they're not as power efficient as they could be, simply because they weren't developed to be power efficient. They were developed for static applications. So we developed our Tarvos ASIC with the main goal being power efficiency, and we did in fact achieve sub 1 milliamp of current draw.
So that point, that 1 milliamp of current draw, is that at some specific level of sound output? Are you trying to say that's kind of irrelevant at that point? It's just you're just going to have a fairly constant energy consumption by that amplifier system. Yeah,
that's measured at like 94 decibel output with our speaker. If you go to extremely high output levels, at some point the voltage range of the class H will change, and then it draws a little more, a few percent more. It's not like 1 point something. But in standard use case where you play 94 decibel at 1 kilohertz, or as an IC noise or something like that, it draws less than a milliamp.
Awesome.
Which is, might we say, it is awesome indeed.
Yeah, you're looking for low power consumption Bluetooth devices. So generally, it's not a huge issue if people are listening at low levels, but as soon as they try and wind it up, that just the power consumption amplifier escalates massively.
Yeah. And it is, of course, a big topic for hearing aids. OTC hearing aids are not typically worn the whole day, because it's more like glasses. You put them on when you need to, and you put them off when you don't need to. But still, you want your hearing aid to last longer than 3 or 4 hours. You want them to last, ideally, at least a working day. So power consumption is a very big topic there as well.
Okay, good.
All right. So yeah, it sounds like you've I heard about the two-way systems modules coming down the pipe. It looks like you've got some pretty heavyweight partners there. So that must be exciting in terms of commercial growth. Are things translating? Is there anything that you can mention that we might find your technology inside today? Any?
So the modules are in the sampling stage. You can imagine we're talking to a bunch of companies at various stages. Some of them at the introductory stage. Some of them, product ready. You will see something soon. Yeah.
Okay. Very good. All right. So, Simon, did you have any more questions?
I've got lots more questions, but I think time's up. I could go on
Sure.
forever.
All right. So yeah, so everybody we'll put some links below for some further information for everybody. And thanks to Andy and Konstantin for joining us today. We appreciate that. And we'll see everybody on the next episode. Thanks, everybody.